slides are available at gotutorial.net, and you can get them. This particular batch is called Lesson 5, which I used to call Level 5, and I haven't actually changed yet. And it is a draft. You guys are my very first victims, audience, as it were. So if something goes terribly wrong, I apologize in advance. The Go concurrency story is fairly straightforward. It's basically based on two primitives and one, control flow statement. They are go routines and channels and select system. I'm just going to jump right in if there's any other. Does anyone have any questions before I get any further? You guys all sorted out? Everybody's got enough food and whatnot? All right. Okay, so Go and concurrency. So Go, unlike many languages, decided that from a philosophical point of view, concurrency is very, very important, and they're actually going to bake in the primitives into the language and the spec and the syntax and all that itself. The primary authors of Go, have written many OSs and programming languages before, and this particular implementation of concurrency is based off a language and a platform called CSP. That was a research project in the early 90s, late 80s, I want to say. So it's not super new, but like in terms of computer science, it's actually well underrepresented until Go itself came out. So that's the kind of the historical of where it came from. It actually works really, really well in practice, especially considering in the 90s, like there was no concept of having 4, 8, 16, 100 cores in a single chip or board. So it was more designed for very, very slow systems to talk to each other, more so than a system. But it turns out it scales really, really well for the current state of the art, which is very, very strong. So Go routines. So Go routines are not threads, and they're not processes, and they're not code routines. And because they're not any of these things, they're different enough that the authors, in order to be completely unambiguous, they invented a new word. It's a cute word, it's got a little ring to it. It's probably not the word I would have chosen, but not the word I would have chosen, but it works. Conceptually, they're lightweight threads, green threads, or like if everyone's used Python, the G event, things like that, stuff like that. Basically, they are. There's a schedule. The implementation has a scheduler, and it multiplexes a lot of these threads onto actual OS processes or OS threads. Go routines share memory. That's somewhat unusual, especially if you're coming from something like Erlang or some of the other, superset Pascal, I think. And some of the actor models, they don't actually have any memory sharing. And this is a good and bad thing. It does have very certain performance advantages, and it does have some very specific safety disadvantages with respect that it's very easy to trump over someone else's thing. So they give you the, as I think the way they phrased it was actually quite violent. They give you the opportunity to shoot yourself in the foot, but also to race ahead like a bullet. I don't know, the metaphor is breaking down. When we talk about Go routines, every Go program is at least one Go routine, the main Go routine. So typical programs end up being more than one. But once all your Go routines are done, like the program's over, it exits and returns typically some kind of value. There's some for the computer scientists or the theoreticists in the room. There's the actual spec definition. Is function call is an independent concurrent thread of control. The thread of control part and all that independent stuff is just the notion that it's running off on its own in the background or in the foreground if you're on the thread. But the important part is the function call, because the way it's implemented is you can only use it on an actual function or a method on an object. So there are real functions. The basic information that you can get on Go routines these are the links there, and if you're following on the slides, feel free to click through. We're not going to do that right now. But the way it looks in practice is it looks like this, right? You just put a Go in front of a method or Go in front of a function, and then it launches itself, launches that method. Instead of launching it on the current, Go routine, it launches it. It basically creates a new Go routine and launches it on that. So the Go routine, the way it normally works is you have hundreds or thousands or tens of thousands or millions of these. They're super lightweight because they're not OS threads or OS processes. Here is an example of Go routine here. Later, what's going to happen is this function. This is just a function that's going to sleep for 20 seconds, and then print something to the console. This is not actually valid Go. I forgot that F for the. What's up?
Can you show here how it shares the memory?
How it shares the memory. We'll get to that. Yeah. Basically, there's just one address space per Go running Go application, and they all have access to the same memory. I mean, it's not. It is safe in the sense that you know you're not doing pointer math and whatnot, but if you have, it shares memory in the sense that it shares memory in the sense that if both Go routines have access to the same variables, they can stomp on that variable at the same time. It's not in the C sense of where everyone's got access to the memory space and they're randomly poking at memory bits like that. It's not that unsafe, but it's not like Clojure where we've got this transactional software, you know, layers on memory or anything like that. Software transactional memory. Thank you. One of the important things about Go routines, and we talked briefly that they're cheap, but the main Go routine is actually very, very important because when the main exits, all other Go routines immediately are terminated. They're just killed. You know, it's like merciless. You know, just get rid of them. Main is very special in that sense. The thing that happens a lot, for example, our previous line of code where we just tried to print something in the background. This particular example here, all main is doing is launching a Go routine and then exiting immediately. And that's not enough time for a print function to actually access the console and print out to the to the terminal, right? So it's not actually enough time for the format package to hit standard output. So this, despite what it looks like, this tiny little Go program does nothing at all. So you will be aware there's tons of ways to mitigate that. You know, the naive way is to just add a sleep statement at the end. If you sleep for 10 milliseconds, that's actually enough time for things to print out of the console. There's a slightly more civilized way of doing that. And there's this notion of something called wait groups. Wait group is a built-in to the system, the standard library. In the sync package, there's this wait group function. And it's essentially a counter. And what it does is you add things to the wait group, and then when you're done, you hit done. But at the very end, there's this notion of waiting. Basically, this line here is going to block until the counter hits 0 again. So it's kind of important, if you create a wait group and immediately wait, like it's not going to wait at all because the counter starts up at 0. Right? So what we're doing here is we're creating the wait group, we add, we kind of iterate through this 5 times. Everybody's seen a for loop, right? Who hasn't seen a for loop? Right, that's just a test. But anyways, we're adding to the, so each time through the for loop, we're adding one, we're sleeping for a random, we launch this Go routine in the background. So this thing launches a new Go routine. It sleeps for some random amount of time, and then it prints, whatever the number is, whether it's 0 through 4. And then when we're done printing, we hit done. And then, but this Go routine stuff, because it's launched in the background, the actual flow of execution is create the wait group, iterate it through this 5 times, launch 5 things, and then wait. So that's the flow of execution of the main Go routine. In the background, everything inside this little function literal here, this little closure here, happens, this all happens on 5 different little background threads. And we can actually see that if I launch our Go Playground. Has anybody seen the Go Playground before? Yeah, I see some nodding there. So you're familiar. Basically, it's this very handy runtime environment that you can actually run in arbitrary code in the background. The links to these here are in the notes section of the slide, the presenter's notes, so you can actually follow along if you sign up for the Wi-Fi if you're using Find or do this at home. So what's going to happen here? So if you're watching this, you would actually see they come out in random order because they're sleeping for just a random duration of time. And then, but at the very end, the program just exits, because it's waiting to the end. It's not super random because this playground is deterministic random number generator. So every time you run it, it's actually seeds with the exact same number. So if you run this on your own laptop, you're actually going to see random order and random times. But on the playground, it's going to be the exact same random numbers every time. So One thing to notice, you talk about sharing memory, is that, where's the mouse? One thing to notice here is that we have to capture I into a new variable. Basically what's going on here is this I variable is shared among all 5 goroutines. But what we're doing is we're creating, the colon equals, for those who are unfamiliar with language, means instantiate a variable named x of the type of whatever you're assigning to, and then assign that thing. So basically whatever I is, we're creating an x and stuffing the value of I in there. So what we really have is 5 different x's and 1 I. So that way here, this actually prints 5 different things. So in terms of sharing memory, like this I is available inside this closure because the closure captures the I, but the I itself is shared. If you muck with the I, like if something in here decremented I, all of a sudden this thing's an infinite, for example.
So if you put I in there, it would print out 5 all the time?
It would print out 5 5s. And you beat me to the punch because they will all print 5 if I is in there, because it kind of looks like this. The flow of execution looks like this, in the sense that I is the gray line. So I. It increments through the for loop. This first half here is a for loop. And then I is kind of stuck at 5. We don't care about it. But what happens here is these launch, at each point through the for loop, we're launching a new goroutine. And the goroutine, because x is, we have 5 different x's, each goroutine is going to have a different value in its own x, as it were. And then, so with respect to weight groups, what we're seeing is that the weight group itself gets incremented through the for loop. And then at random intervals, we get a whole bunch of dones. And then at the very end, it exits. And that's kind of how weight group works. Does that make sense? Can everyone hopefully can see that and understand that? They're not actually that complicated, but don't roll your own, because that's what I did before I realized weight groups existed. What's it?
So x is like local variable inside the for loop.
I'm sorry?
In the previous example. So no, before.
This one?
Yeah, here. So x is just like local variable inside the for loop, right?
Yes. The scope of x is inside one iteration of the for loop.
So
So that's why there's 5 x's conceptually.
Is it kind of similar to JavaScript this and that?
I think it's more like a closure. So
Yeah,
it closes over the value of the variable.
Sort of, right? What's going here is we have 5 different closures, and the closures are capturing the existing scope. So the first time through the for loop, we've got I, which is scope to main. No, I'm sorry. Well, I is basically scope to the entire everybody's for loop. X is scope to one iteration around the for loop, and the closure captures all the way up its scope stack. So it captures the thing in here. It captures its current iteration, and it captures the stuff that's in all the for loops, and then it also captures the weight group too, because we're using a weight group down here. So
I'm not sure what would happen if you allocated X on the outside.
if you allocated X on the outside,
Would you get 5 all the time as well?
if you had
If you didn't
X
use
on the
colon
inside
equals-
and X on the outside,
If you didn't use colon equals on the inside, you use it on the outside.
yeah, you would also get 5s, because that means X is scoped to the main, and then it'd be kind of like this weight group. It's the same weight group. These are all operating on the same weight group, but these are all operating on different X's.
So what happens if you move that line either side of the go function?
This line?
Yes.
I bet that you would get mostly 5s, because the Go, even though they are ultra lightweight, this for loop is going to be faster, because the for loop has got basically an add and a launch, and so the for loop's going to complete all 5 iterations before any of the 5 Go routines actually launch. That's my guess, but
There's no guarantee.
Yeah, there's no guarantee. It depends on your particular how many cores you got running and how many what the current actual implementation, which compiler you chose. But that would be my guess.
So it'd be a good idea to pass it in as an argument to func.
You could do that. That makes a lot of sense. Yeah.
So for
It's
Go,
going to be I is going to be the closure, right? So
When you pass it in as an argument,
It's
right?
copied.
It's copied, because Go does pass by value. So the value of I is copied and not I itself. If you did a pointer to I, then yeah, then it would be kind of that sense.
So I have a question. So for x equal to I,
because the way actually declare in that statement is just like every time you declare a new X, right?
Yeah. So there's two kinds of assignments in Go. There's the colon equals, and then there's just regular equals. Regular equals means I want to take an existing variable and stuff a value into it. Colon equals means, for convenience, I'm going to instantiate a new variable, in this case X, and then stuff, and make sure it's the right type, and then stuff I into that.
Because it does type inference.
Type inference.
Whereas
type,
you could say
type
var
Elijah.
X int.
The
And then
type
you could
is
say X
Elijah.
equals X, and then you do this and I equals something.
Basically, yeah. Yeah, so we were talking about a long discussion on the nuance of X, why we use X. So we saw this already. More things. So goroutines are cheap. We basically talked about this. What I found is on modern hardware, it's basically in the order of millions of simultaneous goroutines without much of a sweat. The thing about being cheap, they all have their own stack, but the stack size is tiny. It's on the order of like 4 kilobytes, I think, so the current 1.2. I think they're using 4 kilobyte stacks. They do grow if necessary, if you're doing a whole bunch of complicated stuff. So, but they basically grow when you need it. The scheduler will run them wherever it wants to. Like you have no control on which core or which processor, which thread it's running on. That's an implementation detail for all intents and purposes. I mean, in certain cases, you can actually configure Go to use one core all the time, and it actually runs everything on the same core, and all the scheduler doing is just like taking turns between them. So it's not necessarily, you're not necessarily getting parallelism, you're not necessarily doing things at the same time.
Even though they're running all the different processors and cores, it's still one shared memory space.
Yeah.
Essentially.
Did they change the behavior? Because I thought default was
The default is to use one core, but you can muck around with that at runtime or with environment variables or with config settings. And there's a bunch of different ways to make it use on more than one core.
And as for the stack size, it's also
The stack size is fixed.
It's about to change too.
Well, they changed it and then they moved it back, and like the past, I want to say the past 2 or 3 release candidates, it's actually gone back and forth a couple times. So they tried to change it to be 8 kilobytes instead of 4, and then they had to move it back to 4 because they found some bugs, and so I don't know where it is. By the time 1.3 comes out, it may be 8 or it may remain 4. I don't know that we know yet as of today. So 1.3 should be coming out in the next month or 2. It's kind of what I heard. So. Yeah, that's like it. Any questions? Or goroutines are fairly straightforward. They're basically just a very, very simple way to say, go do this in the background, and when you're done, you clean up after yourself. That's kind of how it is. Conceptually, it's just launch this on some other, on some other context that's not the current context. Even though you might be doing it on one core, the better conceptualization is that you launch something in the background. And if you do that, you're not gonna run into too many problems. Channels. So the other half of the Go concurrency story is considerably more complicated, and it's not really. There's just a lot more to talk about. I think in terms of slides, we've gone through 12 slides or so. The remaining 30 slides are on concurrency. So if number of slides in a concurrency presentation is any kind of important metric, it's about 3 to 1 in terms of complexity of channels. So channels are basically a built-in native, baked-in type that provides communication between 2 different Go routines. They're a reference type, and we're going to talk about more in that detail. For now, it's just an implementation detail. But conceptually, they're like typed pipes in a sense, like a pipe, like an integer pipe. You can only pass integers back and forth, or a string pipe, or like any kind of complex object, complex hierarchy of objects. You can create, a structure that you want to pass back and forth. Basically, you have to give it a type before you can actually make or use a channel. They are used to safely and atomically send values between 2 different Go routines, and that's, we're going to get more into detail on those. So don't worry too much about the summary here. The actual syntax is fairly straightforward. We use the make command. In Go, there are a stupidly confusing number of ways to make things, like 3. So make, the built-in make is for, as a rule of thumb, slices, maps, and channels. The the built-in new function, new parentheses, is for if you want to make pointers. And then the rest of the time, you usually just assign or use the just make a variable. one thing we didn't talk about is interface types. We talked about that last month, so some of the new people here just kind of take my word for it that interface types are kind of cool. But basically here, what we're making is a channel, you know, this chan int is just a channel that can only pass ints back and forth. And chan shape is a channel that can only pass shapes back and forth. And Quacker is an interface, so it's like a Java interface or Objective-C protocol, meaning that channel queues can only pass objects that implement the quack method. So if you quack, then you can get stuff through this channel. So it's all good.
I was laughing at you. I was laughing. Sorry.
We'll let it go this time. Dibs. The way you actually send messages over channels is with the arrow. And it's like the arrow, capital T-H-E-V. There's only leftward arrow, and I kind of wish I came to this realization like 3 years ago, because for years and years I was using the wrong way arrow and stuffing values in the wrong way because, I don't know, I didn't even think about it. So rule of thumb, if you're not writing a leftward arrow, you're not actually writing go. I don't know what you're doing. You're off on your own thing. But. So to send data through a channel, the arrow is on the right side of the channel variable. And if you want to receive data, conceptually I think of it as pulling data from a channel. The Go authors might disagree with me, but the one way to think about receiving is that you're actually taking the time to pull a value out of the channel. If the right arrow, or if the arrow is on the left side of the variable, then you're receiving a value. And the Go formatter, just to drive all the OCD people insane, there's no space when you're receiving, and there is a space when you are sending. So OCD people beware, Go format is not your friend. There are two types of channels, buffered or
the space at the first, is it always?
This one?
That should be there.
It doesn't matter. Like the compiler itself doesn't care. It's just the formatting tool that will insert the spaces for you. Yeah. The compiler doesn't care. Yeah. It's like Honey Badger.
Is it idiomatic to, like, can you actually write that bottom one?
This here?
Or are you supposed to send that to an underscore?
Oh,
This one here?
Yeah.
No, yeah. This is totally. You see this all the time.
Okay.
Yeah. I mean, you could send it to an underscore, but this is like a whole 3 less bytes. Yeah. Why would you do that? I don't want you to run out of your quota of underscores, right? Bad. Yeah. There's two kinds of channels, buffered and unbuffered, or otherwise known as asynchronous and synchronous, depending on which spec or which documentation you read. The default is unbuffered and synchronous. Synchronous and unbuffered are the same. We're going to talk about asynchronous later. Basically, they just have a buffer inside them, but don't worry about that for now. Just understand that by default, channels are synchronous and unbuffered. Synchronous channels are the reason that the synchronous part of being a synchronous channel is the reason that these channels work so well for concurrency. Basically, when we talk about communication between through channels being atomic, what we mean is that a send operation on a channel is going to block until someone's ready to receive. And similarly, a receive operation on a channel is going to block until someone's ready to receive. So if you got two different Go routines kind of doing their own thing, one's doing some math and the other's doing some reads and some writes, and at one point one of them says, "Oh, I'm ready to send or receive," until the other guy's ready, like nothing is actually going to get sent or recepted. When they're both ready, when you have on both sides of the channel a sender and a receiver, that operation is atomic. Like the entire world pauses so that data can get that integer or that string or whatever can get sent through. The most ridiculous metaphor in the world is like, anyone seen the movie 300? If the sender is a big Spartan with a big beard and the channel is a big hole in the ground and the value is a messenger, right? What he's doing, he's kicking it down the hole, and then he's falling through the hole and coming down the other side. This is synchronization. This is what makes the channel so powerful. And it's a little bit silly, but it actually works really well as a metaphor. Actually, it's very, very silly. It doesn't work. For some distributions. The way it works, just to talk about the blocking in particular, right? If you make a channel of ints and you try and send 42 with it, this standalone Go program of it itself, these top 5 lines, these top 6 lines, basically it's going to block, and it's just going to become the equivalent of an infinite loop. It's just going to sit there doing nothing, and you know, it's not going to relinquish control and everything. It's waiting forever because it's you know, it's the loneliest number. There's no one on the other side to actually talk to. Similarly, like here, if we have a guy that's like trying to get an int, you know, like maybe this guy is the loneliest because no one actually sends him anything. Maybe the sender guy is just desperate. But this guy here, there's no one to receive anything, and he's also going to block forever and hang your app and all kinds of bad things. The good thing about the actual implementation of Go is that you get into a mode called deadlock, and the Go runtime itself kind of knows this, and it'll actually panic your app for you and kind of crash for you because you are, when every Go routine gets into a wait state, and excuse me, if everybody's waiting and nothing's actually happening, and then the runtime understands that and will actually crash your app for you. So when we say blocks forever and the whole thing's hang, that's not completely accurate, but conceptually that's what you don't want to think about. What's actually going to happen is both of these apps will just crash in a deadlock state. So there is that. What do we got here? So here's an example of a non-deadlocked, you know, very, very simple, trivial, for the sake of explanation, example of using. So very similarly, what we're doing is the first thing is, in order to actually use channels correctly, you need 2 different Go routines. So we're going to launch a Go routine, right? And all we're doing is we're trying to send 42. But this particular here is going to hang because, you know, no one's waiting for it. What this thing's doing is it's sleeping for 2 seconds. So even though this takes some number of milliseconds to get started, this is, you know, 2 seconds is a long time. So the main Go routine is just chilling out, you know, taking this 2-second nap. And when it wakes up, it says, okay, I think I'm going to pull a value. I'm going to receive a value from this channel. And again, the channel sharing memory is shared between both, you know, the main Go routine and this, you know, little, you know, split off Go routine. And so once it happens, then, you know, we can print out the number we get, which better be 42, or else something's really wrong with the universe, and then everyone's happy.
You don't need a sleep though, right? I mean, it has to hang the main.
You don't need to sleep. The sleep is just to illustrate a point. Yeah, that's absolutely true. Like, if you didn't have a sleep, this thing actually would be a thing that's blocking while the Go routine is spun up and launched. And then, you know, and it's on the order of, you know, like milliseconds or potentially microseconds, depending on your, you know, your implementation. But that's kind of how that works. So you're right. The sleep is just for demonstration purposes. So what we have here is what I'm calling a random number pump, and it's basically a channel called RNP, which stands for random number pump. And all we're really doing is we're just continuously, in an infinite loop, stuffing in random integers into it. So the way we're doing it is that, I don't know why we're doing this. I only did this because I want to talk about this kind of hypothetical hardware-assisted random number pump. So as you know, or as you may not know, you probably know, because they're all very smart and intelligent people, and handsome, and beautiful. Random number generators in computers are typically, under the hood, pseudo-random number generators, which means they rely on very fancy algorithms to actually create some semblance of numbers that approximate, you know, that feel random to most people. But there are hardware devices that can actually provide true, you know, true random entropy to a number generator and stuff and whatnot. What we have here is a hypothetical random number pump that, you know, we have a hardware method to access the entropy in this hardware device, this hypothetical hardware device. But our problem is that we can only get, you know, we can only have one processor, one Go routine accessing this function at a time. So basically, you know, we want to isolate access. In the old days, we would use a mutex and we just lock and unlock it and wrap it around some nice accessor and whatnot. But you know, this is for the purpose of demonstration. We're not going to use mutexes, right? Because what we're doing here is, the thing about channels is that even if you have 10,000 different Go routines trying to pull from a channel at once, they only get access one at a time. So without really doing too much, we've already isolated access to this get hardware entropy just by locking in its own little closure. So what we're going to happen here is we're gonna seed the random number generator with the hardware device, and then we're going to get ready to send one out. And you know, if there's 10,000 barbarians clawing at the gates trying to get at these, you know, highly desirable random numbers, then what's going to happen is that the gate, the random number pump channel, this channel here acts as a very little gate in that only one of those barbarians can get in at a time to grab its, you know, golden, precious, luscious random number. But that also means that we're not going to have nowhere near 10,000 guys acting on this, you know, hardware device at once. We're going to have one at a time. They're going to hit the hardware device. So this is a way, you know, we talk about synchronization. You know, this is basically without the use of muxes or anything. We've isolated access to hardware, which is usually where you want to isolate access. There are many other reasons to do it. Sometimes it's databases or hardware, but this is a common paradigm. You're going to see this a lot. This idiom is very common and very important. It kind of just demonstrates what you get automatically when you have a channel-based architecture, channel-based design.
I have a question. So how would you do something like a multicast or a broadcast?
We'll get to that.
Can I also ask
Yes.
something? In this one, why is this not hang?
This one here?
Yeah.
Oh, so it does hang until one of the barbarians, you know, tries to pull something.
Yeah, but why the go it is not deciding to kill it?
So the assumption here is that your main routine is running and kind of doing its own thing.
So main didn't hang.
Yeah, main. If main hangs, then Go will kill it. But this function here, the Go runtime is only going to kill the program if all the Go routines are hanging.
Okay.
So right now, yeah,
if this hangs forever, it will be okay.
it's totally fine. This thing's just chilling out on its own. In fact, he's kicking back, taking a break. So no barbarians today. Barbarians have the day off. But you know, the assumption is that the 10,000 barbarians and then the main barbarian are not hung. They haven't yet been caught by the, never mind, the metaphors. So, what did I call this? I called this slide the idiomatic hypothetical hardware-assisted random number pump, just to test the limits of Keynote's ability to do slide titles. But basically, what we're doing here is we're wrapping the creation, and you know, we're wrapping this global variable behind an accessor, possibly in its own file or its own package or whatever. The idea is that functions that return channels is something you're going to see often, because sometimes it makes sense to hide the creation and the manipulation of a channel. You just want people to be able to pull things from it, or you just want people to be able to push things to it.
So you basically created a single.
In this case, it is, but it's not always.
Right.
It kind of depends. I mean, the reason we do have a singleton is because of hardware, right? We are intentionally trying to. If we had, for example, two different hardware devices, hardware entropy devices plugged in, you know, there could actually be, this might be an array of two channels, right?
But then you maybe start two routines.
Yeah, there would either be two of those, or yeah, there's a couple different ways to slice it up and to get access to two, but you could actually have just the one channel and just have, you know, just pick from hardware 1 or hardware 2 randomly, depending on, you know, who's available and whatnot. Yeah. So there's a couple different ways, and we're going to get to that. But for now, just understand that functions that return channels is actually pretty powerful.
We wouldn't even need to be global here, the RNP channel. I mean, you could just make it instantiate it locally and then return it.
Yeah, that's right. I mean, we do have the notion that the closure itself, this guy here is capturing the one, so it could actually just be in there. So that's actually a really good point, because we're only launching one function here, so it definitely doesn't have to be the one. So that's totally accurate. Actually, now that I think about it, there's actually a bug in that program. So version 0.1 of these slides is a little bit buggy. I apologize. So we've been now talking about asynchronous channels up till now. So we're going to take a step back and talk about. I'm sorry. We've been talking about synchronous channels up till now. We're going to take a step back and talk about asynchronous channels. They're actually conceptually similar. It's like a Go routine with just like a little buffer or bucket inside where it can hold stuff here. All you do to make it is just add a little number at the end, comma, whatever the size if you want the buffer. So this here is a buffered channel of ints, of integers that can, you know, that's got a capacity of 2. So the only difference is as long as the buffer is not full, they're not going to block. And this can be useful when you want to you want to be able to either take things in or push things out, you know, without blocking as much because you've got certain kind of restraints. There's a notion of things like if you know, for example, that you have 2 hardware devices, it might actually make sense to make a buffer of 1 so you can handle one and still be able to pull in another. Or I'm sorry, if you have 2 hardware entropy devices, it may make sense to have a buffer of 2 so that you could act on the 2 devices while the third attempt will actually block. So it's just a way of, to some degree, of conceptually, to a metaphor, you're widening the channel, but that's not, it's more of a depth. You're really increasing the depth of the channel. So you lose some of the asynchronous and the atomicity, but it can be useful in a few different places. The buffer capacity cannot change once you create it. You either have to throw away your channel and create a new one or something like that. Buffer capacity is not part of type. So here we're making a buffered channel and we're making an unbuffered channel. And we can actually throw them into the same variable. Like variables, you know, when you talk about the type of a channel, like the buffer itself is basically an implementation detail that the type system doesn't care about and it's not very particular about. It can be a little dangerous, like if you're doing a lot of, you know, variable, you know, assignment jujitsu like this, then you're basically just confusing yourself and you want to be more explicit. You know, good programming means that you're smarter about your naming of this. This is just for example. This is legal, although potentially dangerous. Channel examples. For those who are very, very curious about channels, there's a handful of very interesting examples out in the wild. The canonical example is where's Sagar? How do I say this guy's name?
Eratosthenes.
Thank you. There's the sieve of that old dead guy. And they actually use that example in the spec as an example package. They actually implement the sieve of him in the actual spec, so you can see what that looks like. There's the blog itself, the official Go blog has quite a bit more examples. These in particular are pretty nice. They talk about some. They're not even that advanced. They're just, you know, some stuff that we'll go through the timeout example here in upcoming, but just some more stuff to go look at if you're curious. For what it's worth, channels in particular, and using them and architecting systems with them, there's a big learning curve. You know, it makes sense on paper when you read it. You know, when I first read the presentations on channels, it made a ton of sense. But there is a disconnect between understanding what a channel is and how to use them appropriately. So there is a bit of a learning curve. It took me, you know, years and years, but I'm not that very smart. So you guys are taking much less time than it took me. So I wouldn't worry about it. There is a notion of iterating around a channel, and we do this with the range keyword. For those of you who weren't here for last month when we talked about arrays and slices, this for something, range something, that's the syntax we use for iterating around slices and arrays and maps to get at the key values and whatnot. So the actual syntax is going to be very familiar to you if you've done anything in regular Go. But what we're doing here is basically we can just indefinitely pull values from a channel. So for this random number pump, we are for infinity, because this, you know, we don't have any kind of end statement. We're pulling a value, waiting a second, pulling a value, waiting a second. It's just constantly pulling is what this range means.
So you're doing the range on the channel itself there?
Yeah, it's the actual word range doesn't make a whole lot of sense, but they used it for consistency with the map, you know, iterating around a map and iterating around slices and whatnot. But the actual word range itself, it doesn't mean anything. You know, what's the range of a channel? I don't know. I think they just wanted to keep I think the notion was that fewer keywords the better. So I don't think of it about iterating so much as just you're constantly receiving. Range is a keyword, yeah.
Basically, they're for each.
Yeah. So like if you have for each from Ruby or you know, any of those other languages, it's kind of the same thing. So the one thing you want your for loop to usually do is eventually stop. And we can do that with the close built-in function. There is a concept of closing a channel. Once you close a channel, you can never ever unclose it. But closing a channel will terminate that for range, that infinite loop, as it were. Just because a channel is closed doesn't mean you can't pull from it. If a channel is closed, what's going to happen when you pull is you're going to pull the zero value, which means for numbers, integers and floats, you're just going to get zeros and 0.0s out of it. If you pull something out of a string channel, you're going to get empty strings. So you're going to get the correct type of what you want, but you're not going to get any kind of actual actionable content for the most part. You don't have to close a channel. I mean, it's not a file. There's no notion of closing a channel to clean up before you deallocate something and whatnot. Channels are going to be garbage collected regardless of whether they're closed. If no one's using a channel, the garbage collection system will find it and clean it up for you. So the closing is it's just done for your convenience with respect to like I want people to stop using this channel, and I want to enforce that. Either I want them to stop iterating in it, or I just want them to stop pulling in general, or at least stop pulling useful things because they can always pull zeros.
Isn't that's one way of stopping the blocks? There are no consumers?
Yeah. Closing a channel will actually unblock because people all of a sudden can pull zeros from what previously was a blocking pull, a blocking receive.
Is this a good way to handle signals too? So you can keep the program running until you send a signal and then close the channel and just close down the program?
I've seen it that way. We're going to talk about quit statements and quit channels in a little bit. You could use it that way, but I think it's more idiomatic to actually use the notion of a dedicated channel to handle quit signals. If you want to check if a channel is open or closed, there's this two-element variation of a pull, of a receive. And basically it's the same comma is open. And I think the next example is quote, yes. So if we have a random number pump, what's going to happen here is, assuming that our getter has an actual channel, then what's going to happen here is open is true because we're under the assumption that it's working and we're going to get a random number. So this is actually going to return a random number and it's going to return true. If we close the channel, which is kind of impolite because all the other people might be using it, the next time we do this basically exact same statement, what we're going to get is the zero value and we're going to get is open equals false. So that's just, this is just an example. This is not code you would actually see in real life, but it's fairly straightforward. Okay, so this is the same kind of thing. We're basically demonstrating how what previously was an infinite loop, if we launch a function on some other routine that 5 seconds in the future closes a channel, this thing will terminate and we'll exit out of the app. We'll exit out of the program. And again, there are more idiomatic ways to do this, but it's an easy way to pull things until the channel is no longer useful to you. There is a notion of channel directionality. By default, all channels are bidirectional, meaning that you can push to them, you can send or receive from any given channel. But sometimes you actually want, to pass someone a channel that is receive only or that is send only. The random number pump, it returns the RNP channel. Like that conceptually is a channel you're only ever pulling from, and there's no reason to ever push into it. What does the pump want to do with a number that you give to it? That's useless to me. Stop giving me stuff. But basically, by adding these arrows to the variable declaration, you basically make it so that it's treated as a unidirectional channel. Under the hood, the channels are always bidirectional, but just in the scope of this variable, these channels here are either receive only or send only. So, but conceptually, they're useful more for safety and sometimes for just readability and understandability. Because even though we declared this variable as a receive only and a send only channel, when you can actually assign any channel you want to it, it doesn't, the compiler doesn't actually care. You just have to be a little bit careful about it. These are actually more useful in the context of function definitions with respect to arguments in and return values from functions. You know, when you expect a channel that people are going to send you stuff, you would expect a receive-only channel because you only are doing receiving from it. If that makes sense. Select statement. So we briefly talked about this in the opening slide about the one control flow statement that helps out with stuff. This is superficially it looks like a switch statement, but the big important difference is that every case statement has either a receive or a send. And in practice, these are like 99% they're just receive statements. Like you rarely ever see send statements in these things. They're just not as useful. And they also get a little bit confusing when it is so basically what we're doing here is we make a bunch of channels, and what we're doing is we're just kind of pulling from a bunch of them at once. When you talk about the select statement, what we're really saying is, I want to pull from a bunch of channels, but you know, give me whatever one's ready. Like I'll take whatever's ready. Right? So for example, if I've got 3 goroutines and 2 of them are sleeping, but the string one is ready, when it hits this, when the main, you know, assuming this isn't a main function, when it hits this select statement, it's only going to pull from it's going to pull from the string statement because the string statement is the only one ready. So basically, this is a way to kind of it's like a demuxer in the sense that I'll take whatever I want and you know and get.
Is there any notion of fairness?
Yes, we'll get to that.
So what happened to the default then?
I'm sorry?
So what happened to the default?
If none of them are ready, you're going to get default. So if all 3 of these channels are still blocking, because you know the other, you know the process of the goroutines responsible for sending them are asleep or broken or something, then you're going to get the default statement. And the actual rules are fairly simple. So like we talked about, every case statement must be a sender or receive, and again, they're mostly always receives. When you hit the select statement, it evaluates all the cases. All the send and receive statements are evaluated. So it basically, it's got to check all of them to see which ones are ready. If only one is ready, then it'll give it that one. That's the obvious trivial case. Like if only the string channel has a sender, you know, because remember, you know, the receive statements block until there's a sender, right? If only the string statement has an actual sender ready to send something, then you're going to get this case here, the string case is going to happen. If more than one is ready, it's randomly selected, and they call it fairly, which means, you know, to borrow an iTunes terminal, it's more like shuffle than it is like random. Like, for example, if you've got a case where all 3 of them are ready, you know, the runtime is going to randomly pick one of them. But the next time it goes around the iteration and we get up on this, if all 3 are ready again, it's going to pick one of the other 2. It's more like shuffle in that sense. So it is fair. Like you're not going to get some weird, you know, crazy case where you get 8 of these channel ints in a row just because all 3 are ready. So it's a little bit, you know, it's got a little bit of intelligence to it. If none are ready, default is the case that's actually happens. So if all 3 are blocking, then we're going to get the default case. But the default's optional. If there's no default, then the entire select statement just blocks.
What's like the use case of using this kind of select or
there's a bunch of them. Now you put me on the spot now. We'll get to some of it here.
It's like the center. Anytime you want to like protect a bunch of variables inside their own Go routine, you have to make everybody else send in order to get access to them. So you use one of these to handle all the different types of requests for information that one central object might be coordinating.
So in theory, you should get a channel starvation where it just never gets serviced.
Yeah, you will. Assuming, you know, you don't have something fundamentally broken in the rest of your app. As for, you know, one thing, you know, like the one obvious place I've seen this kind of stuff is like signal handling. You know, when I'm like OS level signals like sigkill and sigint and sighup and things like that. That's actually typically implemented by select statements because each signal comes on its own channel. So you just throw up a select statement with the signals you care about, and then you know you can handle them as they come. I mean, in that case, it's you know sometimes this is no more than a fancy you know if else thing, but sometimes it's actually because you actually want to handle a bunch of different things at once. So there's a bunch of different ways. This statement actually turns out to be surprisingly useful in the context of juggling multiple channels. But I guess you have to kind of take my word for it. select timeout. So here's an example, right? And we talked about a little bit about here. Well, what we do here is we're waiting for an int, and it's going to get an int, but we're also waiting for this kind of timeout clause. Time.after is a standard library function that returns a channel that spits out a timestamp after 5 seconds in this particular case. So what's going to happen here is, even though it looks like a function, this function returns a channel, so we're pulling from whatever this function returns. And we're ignoring the value. You don't have to actually use the value. But what happens here is that we're waiting for unint unless 5 seconds happen. Right? So this is an example of waiting for 2 different signals at once, 2 different channels at once. Does that make sense? What's going on here? And you know, this kind of thing of when you're waiting for a bunch of things and you just want whatever's ready, you're going to use these select statements a lot. Request response. There's this notion of passing a channel through a channel. What we're doing here is you know, who's heard of HTTP? Why are some people not raising their hands? I don't know. Okay. So there's this notion of a request and a response that pretty much everyone's familiar with. Even the people who didn't raise their hands. I know you're lying to me. But what happens here is we're creating a request, and you know, in this case it's just fundamentally a question, like what's your question, or what's your name, and the response basically when we ask something a question is like, well, I have an answer, but who do I send it to? In HTTP it sends it back to the original requester, but in this case what we're doing is we're creating a channel so that whoever handles the request can send the response back on the channel. So this is a channel that you can only send responses back through it. So what we're doing here is this start is the equivalent of our server. What's going on? It's an infinite loop, and all it's doing is what's going on here is that every time, basically it's going to block on this statement here, on this pull, on this receive statement. Right? I guess can anyone see sort of? It's kind of towards the bottom. So it's blocking on this receive statement, and then the handler is going to pull the request out of this channel and then handle it and then do something with it. But it's launching the handler in the background. The main statement is going to look like this, and this is going to be a little small, so I apologize.
Sorry, can I just ask, does it launch the goroutine first, or does it get from the channel first?
It gets the channel first, and then it launches the goroutine.
So it can't actually start the goroutine until it's evaluated all its arguments completely?
It blocks here
Yeah.
on this pull, and when it gets a value, it launches the
Then it will
goroutine
actually-
and launches the handler. It creates the goroutine and launches the handler on the new goroutine. The main function looks like this. First we define a handler, and in this case our handler is kind of dumb. All it says is I don't know the answer to your question, and responds with some arbitrary code. I don't know where that number came from. It just came to me. We make our request channel and our response channel. So basically here we start our server, as it were, and we give it the handler, which is its own little closure, and we give it the request channel. So basically now all we have to do is stuff questions into the request channel, and then magically the answers will come back to us. And the way they come back to us is with this select statement, in which we have a for. Remember that select statements, they only happen once. If you want to iterate around a select statement, you got to wrap it in a for loop or whatever other infinite loop makes sense to you. So basically here what we're doing is we're pulling from the response channel. So we're assuming that somebody is stuffing the request channel, and we're just consuming the responses. Unless 4 seconds happen and then we're quitting. Because I'm tired of waiting for answers. I don't need answers. I don't need your answers anymore. And then in both cases we're just printing out something to the console. And because it's somewhat instructive, let's see if I can use my mouse on the far side. There it is, timed out. So what happened here is we launched the thing that's stuffing questions into our request channel is this little closure here. It sleeps for a second. Excuse me. It sleeps for a second. It stuffs a question in, and then what happens here on the main goroutine this thing is blocking on the select because neither the time after, neither our timeout or our response happens. So, but 1 second later, we're getting the request. 1 second later, the handler. I'm sorry, I'm confusing myself. So what happens here is that we see this at 1 second later, this one pops out. Another second later, this one pops out, and then 2 seconds later, it times out. And because this is really hard to conceptualize, I actually have a slide dedicated to the conceptualization of what actually is going on here. And it looks like this.
Wow.
So so everyone remembers what the main function looked like, right? Keep that in your head as we talk about this.
So can we go back for a second? I just wanted to ask if the 4 seconds starts each time through the for loop, or does it, it looks like it makes it a new 4 second timer each time through the for loop, right?
It does.
Okay.
But in this case, we have a return statement, and so
Right, but it's
Yeah.
not going to like.
if you
only
didn't
wait
have a
2
return
seconds.
statement, this would actually just print out timed out every 4 seconds. So what's going on here is that our main function, the first thing it does is it launches our server goroutine, just for lack of a better word. And then it launches our asker, you know, our little anonymous function here. And then, right around here is when the select statement hits on the goroutine. And what we're seeing here is that it starts pulling on the response channel, and no one's ready, no one's asking any questions, so there aren't responses yet. But it also launches the timeout, the timeout. The time.after launches its own goroutine, so that is under the hood within the standard library, so we don't actually see or have any control over that. We just kind of have to trust that eventually we're going to get it. So this is not a goroutine that we created. The standard library created and managed it for us. So our question asker kind of sleeps for that first second, and then what happens here is it sends "What is your name?" you know, to the server. The server gets that, it handles it. It says, "I don't know the answer to what is your name." You know, because it launched its own handler here, and it says, "I don't know the answer to your name." And then the handler itself sends the response back over the response channel. And remember, our main had that select statement at the bottom that we're iterating around. At this point, the select statement says, "Oh, someone sent me a response. I better print that out." So this is where it prints out that first line, where 404. I don't know the answer to what is your name. And and so then it's happy. Then we're stuck in this waiting mode again. We're blocking on the select statement again. And what happens here is we wait for another second, and the asker asks the second question: "What is your quest?" And so the server, of course, launches another goroutine to handle. It handles it and says, "I don't know the answer to what is your quest." And then again, well, the select statement picks that up. Oh, there is another response available for me to do. And so it prints out the response here. And then at that point, our anonymous function is done. This goroutine exits, and the garbage collector picks it up and cleans it up. The main routine at this point is just sleeping for 2 seconds, saying,
No, but it's got 4 seconds here. That's wrong.
Actually, you should have 3 timeouts there.
I'm sorry, what?
You should have three instances of timeout in main should go all the way to 6 seconds.
You're right. That is correct. There's a bug in my
But you could make it. I mean, you could make it conform to this diagram if you moved the
Yeah.
outside the for loop.
Yeah.
The timeout.
So this is
state has
actually
to go.
4 seconds of waiting because I screwed up the select statement. But anyways, there is eventually what happens here in this space. What actually happens is, since no one's asking, it just kind of chills out for a while, and then eventually it times out, and that's when it gets a timeout. Main hits says the main prints timed out and main returns, and at that point the server is also terminated because
Doesn't it evaluate the select? Doesn't it evaluate the after the first time through the loop?
yeah.
So if I put 5
every time.
if I said every time through the loop, that
Yeah,
doesn't
look
make
at the
sense.
loop. Yeah, this is a subtle thing. It took me a long time to figure this out, but it's worth looking at.
After you finish up that loop, that select,
Oh.
before that
Oh, I
timeout
see.
after is out of scope.
Yeah. So what I really wanted here is like this.
It's subtle.
Timeout chat. This.
It's not on the screen right now.
So it goes through the loop and
So the select is only executed once each time through the for loop.
Oh, I get it. That's
Yeah. So the diagram I drew, this is actually the code that makes sense.
Because something fired, it exits out and it runs the loop again.
Yeah.
As long as something responds,
Right,
it will keep
exactly.
running the loop.
So in this case, we have one timeout channel, and then it's not constantly being evaluated. In the code I had before, every time the select statement fired, it restarted, it created a brand new timeout channel, and we basically threw away the old timeout channel. So this actually matches the picture, for what it's worth.
But sometimes you want, you know.
Yeah, and sometimes you want it this way, and sometimes you want it the other way. So it's just
So the other way would be how you implement a global timeout for no communication at all.
yeah. So if I have 5 minutes of no activity, kill the system.
This should be right.
This is
No, no, 'cause
after
this does it-
this is
this
after
does it
4
no matter
seconds,
what.
no matter what.
No
kill.
matter what, kill it.
Yeah, but if I had it in the old way,
This
That
is
is
probably
a
less
little-
common.
I guess I'm
No, but I
confused
mean,
then.
global is, what I'm talking about is the whole select channel, no matter what happens, it will stop waiting for stuff after 4 seconds.
That's the-
Whereas in this one, no matter anything happens after 4 seconds, it'll show. Well, no,
Yeah.
the one before the
so the old one,
Yeah.
after 4 seconds, no matter what,
Right.
everything would die. And that's the diagram I drew.
Fixed one.
Yeah, this one here is basically every time around the select statement, you get a brand new timeout channel, and the garbage collector basically cleans up the old ones.
So because nothing's there to receive it, it just goes away.
Yeah.
Interesting. A full seconds. Half to no activity.
Yeah.
The other one is everything that happens in the full seconds.
Yeah. So you can we should actually be able to count. If you're, yeah.
I mean, to be clear, it still blocks on the receive until.
So here, so 1 second in there, 2 seconds in there,
1, 2, 3.
4 there.
Yeah.
Does it make sense?
Yeah, that's subtle, that's not obvious.
It is a little bit subtle, and again, there is a little bit of learning curve.
Because like,
Going back to the question about, going back to the thing about garbage collecting, channels which don't have no receivers.
Yeah.
Will those dead in the original code chapter, will those timed out afterwards be garbage collected before they even fire? Or will a bunch of them just always sit around if you had a really heavy server, it would just
I don't know. It depends on the garbage collector. I can't speak to the inner workings of the garbage collector. I don't know enough about it.
But
Maybe.
conceptually, those things could have side effects if they run. So those channels which are not receiving.
So what's going on here is that the second time through the select statement, though, you no longer have any references to that channel at all. So it doesn't matter if you send something through it. Actually, no. They're going to stay alive because the standard library is still waiting to send something through it, even though there's no receivers. Once the standard library sends through it and then finishes, that terminates itself, then all of a sudden the channel is marked for collection. Because even though it's waiting, it's stuck. There's nothing for it to do anymore.
So this is maybe a dumb question, but garbage collector is started by default.
Yeah. It runs always.
You have no choice.
Very little control of the garbage
I
collector.
think you can pause it, like, temporarily, but yeah.
Yeah.
Or you can force a collection, but
You talked briefly about quitting stuff. There is actually a very idiomatic thing. If you remember our starting the server function that we wrote, we gave it a handler and a request channel to stuff questions into it. There's also this very, very common notion of a quit channel, where you can actually use a channel to quit. Here I just use a return statement here, but it could also be, you could also break out of the. If you do just a naked break here, it's going to break out of the select statement, and that's usually not what you want. You want to break out of the for loop, and you have to use the label syntax to do so. But I just used a return here because it was easier to type on a slide. But this notion of a quit channel is the most common way I've seen to quit, other channels that are looping infinitely, even more so than closing the request channel or something like that. So that makes any sense. Yeah. So we're almost done here. Putting it all together, the channel send and receive gives you, very atomic communication, and it's a good way to get two different goroutines to line up and just kind of be in the same state. The select gives you that kind of multiplex, typically receiving. You can also do sends, but again, I found that I almost never use them that way. The channels as a first-class object means that you're constantly passing them around. You can have functions that return channels that pass channels through them, and or channels that pass structs that have channels through them. Channels of channels is a surprisingly powerful mechanism once you wrap your head around kind of how things work. And there's a lot of stuff. The Go developers have this notion of do not communicate by sharing memory, rather share memory by communicating. And so what it really means, instead of having a piece of memory that you share and kind of have a mutex around it, you know, you actually just use channels to pass around that important piece of memory, and whoever has access to it can use it, and when they're done with it, they stuff it on another channel, and everyone else blocks while they're waiting for it. So, you know, at a high level, that's really what they're talking about there. There is tons and tons and tons of words written down by very, very smart people on this topic here. And this slide's kind of tiny, so you can grab the slides on the website for now. But the shared memory by communicating is described in detail in a slightly older but still very accurate blog post. There's a couple of code walks about concurrency. There's actually a very good presentation. There's a handful of presentations. Some of this here is a direct YouTube link, but some of these other blog posts here are links to actual other videos by the Go authors on the topic. This here is a really interesting blog post on timeout patterns and some of the other, you know, fan in, fan out patterns, and some, you know, you can think of it as like topologies of how to, you know, manipulate, you know, how to kind of get the behavior you want with different patterns of channels and whatnot. Pipelines is another one kind of similar to that. And then the effective Go document is just a well-written article, and it's a must-read for anyone interested in Go, period. It's just got tons and tons of best practices and kind of, you know, smarts and lessons learned. And there's a very specific section on concurrency. It's got about 5 or 6 sections in there, so that's, you know, more places to get info. And then lastly, again, I found that channels in general, just the way to think about them, had a fairly steep learning curve. And again, you guys are all smarter than me, so it's worth your while to kind of figure this stuff out and kind of have a little practice with it. There is one notion that performance is a little bit hard to predict. Even though channels are very cheap in general, they're not free, and there is some overhead. And if you're launching millions of them, that, you know, you're going to see some stuff. In some cases, it actually makes sense to use an old-fashioned mutex. The sync package in the standard library has some of these, you know, the standard, you know, do this just once no matter what, or mutex and read-write mutexes, things like that, and a conditional mutex, conditional primitive and whatnot. And sometimes it makes sense to use the old-fashioned primitives. If you've got a very, very simple value that you just want, you know, to occasionally lock around, sometimes the mutex is going to actually be quite a bit more, I don't know, safer or performant than using a channel-based architecture for the synchronization would be. So, in general, the simpler you want to keep your things, then sometimes the general rule of thumb is if it's very, very simple, a mutex makes a lot of sense. But the more, once you get to medium or high level of complexity, then channel architecture is going to be well worth the effort. You know, mutex spaghetti, if you've ever tried to debug any of that stuff, is a nightmare. That's all I have. A couple of notes. The slides are available at gotutorial.net. The content, quite a bit of the content of this and all the content from last month was inspired by a very old set of slides that Rob Pike wrote for a 3-day Go course that was written long before Go 1 ever came out. So some of the terminology and a little bit of the syntax is considered out of date, but I still find these to be, you know, some of the best references. So at a high level overview of language, as long as you kind of keep it with a grain of salt that some of the terminology isn't quite up to date, then you can check those out there. Yeah, and thank you guys for coming. That's all I got.